start, yes, the recording again. Now the multiple choices are posted in the chat. So maybe you have access to it only if you're already logged in when they are posted. That's not clear to me, but however, they are also on the screen now. So let's have a look at this one. And for today, there is no poll ready because it needs some adjusting, which I cannot do on the go. So let's say we do it together, okay? So for example, about this one, just write in the chat if you think it is A, B, C, or D, and so we see then together what is the right answer. So just let me know what you think. And by the way, also if you can hear me, because that's interesting too. It's a good thing to know. Okay, good. So you can hear me, and if possible, just post your probably, yes. What do you think the answer to be in the chat? A, B, C, D, let's see. So we have, yeah, B and C for people. Well, the poll maybe is easier to manage in this way. We'll work through it. So looks like there are two preferred options. Let's see, B and C. So there are two preferred options, say option B and option C. Okay, let's see together how we can decide which one is correct. So first, what we are given is a vector equation, okay? So there are two ways in which you can deal with this vector equation. So here it is. One way is to do the following thing, to say, well, I'm looking for a vector x, so it's going to be something like ai plus bj plus ck. Then you plug it into the equation, so you compute x cross I, which is what? It is a I cross I plus b j cross I plus c k cross I. So the first one I tell you because it's easy. This is vector 0, right? Okay. Then what about j cross I? What is j cross I? What do you think? What about j cross I? So j cross I is actually f minus k. Oh no, it's not working. No, it's working. No. I was looking if it was a quick way to repost the quiz, but no. You have to do it by yourself. So Emani, yes, yourself. Okay, so j cross I. J cross I is going to be some k, right? So you just to decide if it is k or minus k, and as many of you said, it is minus k. Just remember the round table trick, right? So the round table trick for which you go this way. So whenever you cross product two of these, if you follow the arrow, you get plus. If you don't follow the arrow, you get minus. And then the last one, I'm mistaken, sorry, this is cross I. So thank you. So what is k cross I? Well, we know it is going to be j, right? Okay, so when we compute x cross I plus I, we will get minus bk plus cj plus I equals 0. So look at this equation now and tell me, what are the solutions Solution means find A, B, C in R, right? Solve means this, to find this A, B, C in R. So what are the A, B, C that makes this 0? What do you think? Well, if and only if they are 0, if you put A, B, and C equals 0, what do you get here? You get I. So the point is that there is nothing multiplying I, so there is no way to produce I. Yeah. So what is the conclusion? The conclusion is that no solution exists. So the right answer is this one. Okay, the equation does not have solutions. Okay, because A is not appearing in what is written in the green box, so it's playing no role. Okay, there is also a quicker way of doing this. So I'd like to show you. The quicker way of doing this is the following. So look at the equation. It is x cross I plus I equals 0. And now I ask you, look at this vector here. No. Look at this vector, the vector here. So what is special about vector x cross I? So let's see, Giancarlo Herrera, we can rewrite. Yes, in some sense, you are correct. Thea Armouche, yes, what I'm writing, I will upload the file which are here in the notes. Well, you will see them now. Yeah. Yes. Okay. Looks like many of you have the right idea. So what we get here, whatever this vector here, call it y. Y has many properties, and in particular, y is orthogonal to I. Right? This is one of the properties of the cross product. So if it is orthogonal to I, it means that this is I, and vector y lies in a plane orthogonal to I. So vector j is in this plane somewhere. In particular, also note this is the x equals 0 plane, right? And so they are never parallel, so you will never get 0. So you can also say that no solution exists just by looking at the geometry, okay? So this geometrical picture means no solution exists simply by thinking, okay? So you see this is something which happens kind of often. Sometimes thinking allows you to compute less, which when you do, for example, multiple choices question like this one, saves you time and maybe it will allow you to get through more multiple choices thinking about the solution and so having a proper idea of the solution. Let's see, Alberto Zebio says, for B and C going to infinity, could we say the equation is satisfied, or is it more complicated than this? Okay, so you're wrong. Well, A and B are real numbers, so they cannot be infinity, but the point is that you can never make it 0. Okay, so now let's have a look to this question 4, in which we have this nice 2x2 matrix, and there are these 4 options. Then let's see what you will get. All these files have been posted in the chat, so you can find it above. Okay, so if only one person cannot hear, try refresh. That's the only thing I can suggest. If everyone else can hear me, well, Yes, it's a good idea to ask to share them again because I cannot easily do it, I think, but we can try. Let's see. Okay, so you are doing it. Yes, if you do that yourself, is easier because to me, I have to stop writing. Okay, let's think about question 4. Let's think about question 4. As soon as you have a possible answer, let me know. What do you think is here? The matrix A is not diagonalizable. Oh, sorry, I picked the wrong one. No, sorry, my bad. Nope, wrong one. This is too advanced. I picked the wrong file, sorry. So we have to move to the next one, okay? Well, you will be able to do this, and maybe some of you can do this now, but this will come in the future. So this is a preview of what we can do in the few weeks, sorry. The one which should be here is this one, yes. These 3 you can do. You can do all of them. So I suggest you start with the previous one, just thinking n equal 2 or 3, okay? N equal 2 or 3, because these are the cases in which you can compute the determinant and you know all the rest. So if we want to play together, let's say you start with question 6, and you let me know what you think about question 6. People who are quicker, faster, already did it, they can move to question 7, 8. But I like to see in the chat what you think about question 6. What is the right answer to question 6 in your mind? What is the right option? Okay, so let's see. What is the right option here for question 6? A, B, C, or D? Let's see. Also, a comment here, you see, then it is necessarily true. It means that it is true for all matrices A and B such that the determinant of A squared is equal to the determinant of B squared equal 1. Okay, so we have Alberto Eusebio suggesting that this is the right option. A transpose times B cube is invertible. Okay, so everything is contained here. So let's say what we can say about this. So let's see if I can make a little bit more space available. No, let's see. Let's see what we can do. Yeah, I think I can do this. I can go here, make a new page, Yes, then I can put it here. Yep. So we will have more room for this too. And then we go back to the previous one. Yep. And we just cover these two. So we can just solve the other one. Okay, good. I'll do that while you think about the answer we got. Okay, so that's a preview. That's something we are going to see in the future, but not so far future. A quick note is that the determinant of a square is equal to the determinant of everything square. This is something you can do, for example, by two matrices. You can check for 2 by 2, and we will see it in general. So in our situation, this means that the determinant of A is equal +1 or -1. And similarly, the determinant of B is equal +1 or -1 because they have square 1. In both cases, we can say that A and B are invertible. So this means that there exist A-1 and B-1. Okay, so if A-1 and B-1 exist, now probably you can see why two people, Alberto Zebio and Soheila Amri, say this is the right one. So I ask them, what is the inverse of A transpose B cubed? So they say that that matrix is invertible, right? So what is the inverse of A transpose B cubed? Let's see if you can tell me. What is the inverse of this matrix? How can you produce the inverse? Well, using the fact that A and B are invertible and they have an inverse. Can you find a matrix that multiplies that one into the identity? Yeah, exactly. So the idea is, well, I want to multiply a T transpose B cubed into the identity. So the first thing I can do, for example, if I multiply to the left, is to say, well, I want to multiply by the inverse of A transpose. If I do this, I will get the identity here, and then I will get B cubed. Then once I have B cubed, I just need to multiply by the inverse of B cubed, and I will get the identity. So if I take these two gentlemen here, I will get the answer I want. So here we can write this is B cubed inverse A transpose inverse. And now we already saw together what is the inverse of the transpose. It is the transpose of the inverse. And then we have to ask ourselves, what is the inverse of B cubed? Well, it is not probably a big surprise. It is the inverse of B 3 times, meaning that if I multiply B cubed, by B-1 3 times, I will get the identity, right? So if I multiply B cubed by B-1, 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 I will get exactly what I want, because this is going to be B squared, this is going to be B, and finally you get the answer. Okay, so this is why this is why, if we go back a second, A transpose B cube invertible is the right option, okay? But it's also a good idea to see, for example, why all the other options are false. That's a good exercise for you to see why the other options are false. So for example, this says that the determinant of A plus B is equal to. How do you prove that this is not necessarily true? Well, you have to produce an example of two matrices such that they have determinant plus or minus 1, as it is said here. And when you sum them, the determinant is not 2. Can you do that? So let me write it here. So about A, say to show this is false, false, find A and B, determinant of A equal plus minus 1, determinant of B equal plus minus 1. Remember, the determinant you can also write with these vertical bars, and determinant of A plus B different from 2. If you cannot find them, well, then option A is correct. So I ask you, can you find two matrices having this property such that their determinant is plus or minus 1? And when you sum them, you get something of determinant different from 2. My suggestion is go for small matrices, 2 by 2. Pascal-Ariaki is a very good idea. Yeah. So Pascal-Ariaki suggests, well, I just take the identity 2 by 2 for both of them. So this is just a matrix 1, 0, 0, 1. And it is of determinant 1. So it is in this situation. Then I produce A plus B. And in doing that, I get a matrix 2, 0, 0, 2. And what is the determinant of A plus B? Well, I think almost everyone knows this is going to be number 4. So this is why option A is wrong. Okay? Sofia Carnau proposed another counterexample. So this is a counterexample. Because it shows that even if you have the hypothesis, here are the hypotheses, the thesis does not hold. So it is a counterexample. And you should do the same if you want to really see if you can do this kind of multiple choices. You should also take this one and see that they are false. Okay, that's a very, very good idea. Probably now is not a good idea to do it in this precise moment. It's more important if we proceed, but I recommend you try. Then you can go to the tutors and show what you got. You can ask them if you didn't manage to, or you can also ask myself. Asking the tutor is more useful for the reason that is the following. They are third-year engineering students, so yourself in 2 years, and they can give you many useful suggestions from a different perspective compared to mine, for example. So if you get to know them, even if through a computer, is very, very useful. Okay. Now we proceed in the same way. We have a look at 7. And let's see, what do you think about 7? So what is the right option? We'll be back in a second. So what is the right option for 7? Here it is. So what do you think? You have these 2 lines, Oh, again, sorry. I took the wrong file. Yes, this is too advanced again. This is in 2 weeks. Maybe people can already do that. But that's something you can see when you do multiple choices, okay? Something about computing the distance. Number 8 is the one I was planning to ask you to do. So forget about number 7. We do number 8. But in the meanwhile, there is a question about from Paolo Lovera about b3 power minus 1. Yes, I can do that. In the meanwhile, you can think about 8. Well, the idea is the following, that the inverse of b cube is the cube of the inverse, simply because b cube is b times b times b. So if I multiply b cube by b minus 1, what I will get? Well, I will get 1 less b here, right? I will add b squared. And then you repeat it, because then b squared is just b times b. I multiply by b minus 1, and you keep going, okay? And this is why you have this equality about the inverse of a power, which is the power of the inverse. But now let's think about number 8. So you have 3 planes, and you want to know what is their intersection. Okay, so Beatrice Tomatis has a suggestion for B. See, she is suggesting that you get a plane. So visually, if this is true, you have 3 planes and when you go intersect them, you get 1 plane. In order for that to be true, all the planes should be equal, okay? I don't think they are all equal, right? Beatrice Tomatis, what do you think? Are all the planes equal so that when you intersect them, you get a plane? Probably not, right? Probably not. It's probably kind of obvious that alpha and beta are not the same. Okay, so I think that this one we can delete, and we can say, well, this is false because alpha is different from beta, for example. And so the intersection is not a plane. Then in the meanwhile, people got more convinced about getting a line as the intersection, okay? Someone also says, well, it is a point. Well, let's see how we can do that. But how do you decide? Well, there is one precise way, which is solve the system. What system? Well, the system of equations given by alpha, beta, and gamma. So x plus z equals 0, y equals 0, and x plus z, plus y plus z equals 0. Well, I write it in matrix form, but probably here most of you already saw something interesting. So matrix form, 1, 0, 1, 0, 1, 0, 1, 1, 1. Just by looking at this matrix A, since the system is homogeneous, is enough to look at this one, I think you will all agree that it is row equivalent to the matrix 1, 0, 1, 0, 1, 0, 0, 0, 0. Right? By performing what elementary row operation? Well, simply row 3 goes in row 3 minus row 1, and then, well, I was too quick. Let's say there is a 1 here, and then I make another step by saying row 3 minus row 2, right? So I do row 3 minus row 2. And so I got these matrix here, this matrix B, which is row equivalent to A. And from what we saw yesterday, no, probably with you was 2 days ago, sorry. Solving this system is the same thing as solving the system. So this is the system AX equals 0. I can solve the system BX equals 0. And the system BX equals 0 is just X plus Z equals 0, Y equals 0. And how do you find the solution set of this one? Remember, we have to look for a small identity matrix. Here it is. It means I can compute X and Y using Z. So the solution set is given by the triple X, Y, Z, such that they are equal to minus T, 0, T, and T is a real number of my choice. Simply, I did here X equal minus Z. Z you call T, and then you get this shape for the solution set, okay? Yes, in other terms, the third equation was redundant. Yes, the third equation was redundant. Also note, that's probably a good thing to note, this is the linear span of the vector minus 1, 0, 1, the set of all multiples. Okay? From a geometrical point of view, what is this? Is a line. Line through the origin with direction vector, which you saw here. And so this is true. This is true. Geometrically, how is the picture? Well, the picture is simply like this. There are 3 planes which have exactly one line in common. And the line is precisely the one we computed here. So here is the line we computed, the intersection of the 3 planes. Okay. Any question about how we solve this? And since the intersection is a line, it's not empty, it's not a point. Okay, good. Let's move to this one, in which you see you are given what people will call a family of lines. So there is a parameter. And we get not just one line, but many, many lines moving around. And then there are questions about these lines. And you see all the words that appear, skew, parallel, coplanar, orthogonal, they are words you know. So take some time, compute this, and see what is the right answer. Gabriele Taricco has a funny question from my point of view. It says, what would be the difference if I wrote T0 minus T? You mean the minus in the other one? Well, let me ask you the same question. Will the solution set change? Or is it the same? Basically, Gabriele Rico, what you are saying is, this is the line. What if I pick this direction vector, or I pick this one, or I pick another one much longer, or another one much shorter, right? The line is always going to be the same. So this is the linear span of 1, 0, minus 1. This is what you wrote. But it is also the linear span of, if you want, 100, 0, minus 100. Or small numbers, if you wish. What is not changing is the line. That's a very crucial step. So your question is very nice, because points out first, notation, names you give to things is not important. And exactly, Ishanpoon Manikandan says the span does not change. And that's the point. The line is there. The way you present it is your choice. You're actually free to present it in many different ways. And there is no best way. It depends on what you have to do. Okay, now let's think about this number 7. And I wait for you to give me some ideas about what you believe to be correct, okay? Some ideas about what you believe to be correct. Okay, let's see if you have some nice ideas. So we have basically C, and then we have a funny remark by Cesare Piemontese, which says, is true in any case. What do you mean? Is it true for all values of t? Just for me to understand, Cesare Piemontese, you mean is true for all values of t, or you mean something different? Okay, so Cesare Piemontese says that even more is true, that for all values of t, these two lines are coplanar. Okay, so to have coplanar lines, what do we need to have? We need to have either they are intersecting, or to be coplanar, they are parallel. Okay, so intersecting or parallel means coplanar, right? That's one way of seeing this. This is one way of seeing this. So what you can do is to show they are either intersecting or parallel for all values of C, and you will show that they are coplanar. So let's write down our lines. So line ST as a system is given by something like x equal y and y equal t z plus 2t. Okay, now let's think for a second. You see, this is a plane not depending on t. So what Cesare-Piemontese says is true, because if you call this plane alpha, then alpha contains st for all t. So they are always going to be coplanar, right? They are always going to be coplanar. This is something you can see just by writing down the line as a system of equations. If you don't realize it, what you will do is, well, I have to see that they intersect or that they are parallel. So we are speaking about line S0, which is x equal y and y equals 0, and line ST, which is the one we wrote before. So this is x equal y and y equal tz plus 2t. So for example, what is the direction vector of this line? Well, it's easy to see what is the direction vector here, because you see the line is already given in parametric form. It is x equal t, sorry, it is x equal 0, y equals 0, and x equals 0, y equals 0, and so z can be anything I want. So the direction vector is 0, 0, 1. Basically, this line is the z-axis, right? And what is the direction vector here? Well, again, the line is given in parametric form, x equal tz plus 2t. Remember, t is fixed, y equal tz plus 2t, and z is equal to a parameter, call it L, which is moving. So the line parameter is L in this case, is not t, because t is already taken. And so what is the direction vector here? Well, the direction vector here is given by the coefficients of t. Sorry, the coefficient of L. So it is 0, 0, 1. Right? So you see, these lines are always parallel. Okay? So, oh, sorry. Sorry. You are correct, Alberto Eusebio. You are correct, because now that z is equal L, I have to do my job correctly. So it is TL plus 2t. So it is, thank you, TT1, sorry, TT1. So you see, it's not true that these are proportional for all t. So it's not true that the lines are parallel for all t. What is true is that they always intersect, okay? No, I'm answering to Pascal Riaki. I'm saying that the line ST is contained in the plane alpha. So there is a fixed plane, alpha, and this contains ST for all t. Because you see, here is the plane alpha, okay? So the plane alpha contains the line for all the values of t. Yeah. Okay, then now we have the two direction vectors, okay? And we can go here, for example, you see there is a question about orthogonal for all values of r. It means that 0, 0, 1 dot a1, which is 1, should be 0 for all value of I. So they are never orthogonal, for example, okay? They are never orthogonal. And if you look at this one, it says there are parallel for all values of A, which means that 0, 0, 1 cross A1 should be 0 for all values of A. But this is not true, right? Just take A equal 1 is not true. And about the first part, being skew, well, they cannot be skew because they are coplanar, okay? They cannot be skew because they are coplanar lines. Okay, so this is what we can say about these kind of question, okay? These multiple choices. Okay, so you see, some of them can be solved very, very quickly if you have the right idea. If you don't have the right idea, you can solve them still, but maybe it will take you a little longer. How do you develop the right idea? Well, by studying the theory, trying to, as say, think out of the box, try to produce some smart argument, usually that is quicker. Okay, so we went through the multiple choices we plan to see, because two of them, you see this one, we cannot do. So now we did the last one. And now we can go and see some exercises from the LAG X file 7-8. So let me know if you have some exercise in particular you want to see. If not, I will just proceed in order one by one. Okay, any preferred exercise from exercise sheet LAG 7-8? So this is number 3. No, this is not number 3. Okay, but the further exercise will have answer, Erfan Kurushfar. They will publish 2 weeks after they appear in the classroom. You will see them in the materiale, you will find a folder. So I think it's best if you try to do that a little bit by yourself, ask the tutor and so on. Or if you really want to know now, you can email it to me and we can discuss it. But for now, it's from the exercise sheets. I prefer to. So I pick one. I proceed in order, 4.1, and I pick just the right one. So we are asked to decide whether these two are row equivalent, where A is something like this. 1, 2, 3, 4, 5, 6. And B is something like this: 1, 2, 3, 0, 0, 0. Remember that being row equivalent is the same thing as saying that I can obtain A from B by applying some sequence of elementary matrices, right? So what do you think first? Is the answer to this question yes or no? Can we find these matrices ER, E1 such that from B I obtain A? What do you think? Pascal Riaki says the answer is no. And let's see, I know it's difficult, but can you explain why the answer is no? Any one of you, Pascal Riaki or? Okay, they don't need to be, well, multiple. I hope you don't mean scalar multiple. So what is the idea? That's true, the answer is no. The fact is that whenever I multiply E times B, by the way the product works, okay, by the way matrix multiplication works, so A, B, C, D, what will happen? Well, something will happen to the first row, which I don't care now, and then something will happen to the second row, which I care. And the second row comes by the second row of the matrix C when you do multiplication column by column. So as many of you said, they are not multiple. It simply means that you get 1 times C here, 2 times D here, and 3 times D here. Okay, and then you have to ask yourself, can I find C, D? Sorry, I made a mistake here. Is always C. Is always C. So then I have to ask myself, can I find C in R such that 4, 5, 6 is equal to C, 2C, 3C? And of course, the answer to this question is no. I cannot do that, right? I cannot make this happen because C must be equal 4, but then 2C is equal 8 is not 5. So this is not possible. There is no way to produce. And we'll see the reason is, as a preview, is related to what is called rank. This matrix has rank 2, while this matrix here has rank 1. Oh, now I see what Giancarlo Herrera meant. Yes, you cannot go from A to B. That's another way of saying that. Good. Let's have a look to the third one. So 413. So this was 41 first part. Then let's see quickly 41 second part. We are asked the same question. Is it true that these two are row equivalent, where A is 1, 2, 3, 4, and B is 1, 3, 2, A, and A is a real number? So the answer to this question will depend on A, very likely. There will be some values of A for which the answer is yes, some values of A for which the answer is no. Maybe is always yes, maybe is always no, but we need to find out. And what is the idea? The idea is that, you know, to prove that they are row equivalent, you can either go from A to B or B to A in one jump, or what I can do, I can change A into a matrix A1, and then I change it into a matrix I change A into a matrix A1, then I change it into a matrix A2. I keep doing this till I get a matrix AR, and then maybe I can do the same, changing B into matrix B1, then into matrix B2, keep doing it, then you get a matrix BT, and if these two are equal, then I can say that by transitivity property, A and B are row equivalent. If I can never do this, then they are not row equivalent. Okay, so what do you think? For what values of A is it true that A and B are row equivalent? Well, when you learn Cesare Piemontese, you have to do experiments, right? This is experiments. And then there is theory telling me that if I have this chain, then I can do this. So the idea is, can I always find versions of A and B which are easily compared, right? So it's not exactly going by trial. It looks like that to you because you just started, but there is a process here. Try to get them into a shape in which it's possible to answer just by looking. And what shape can we choose? Well, the one with a lot of zeros. So what will be a good thing to do is to say that A is equivalent to something like this, 1, 2, and then let's tell me if this is convincing you. 3 minus 3 is 0, 4 minus 6 is minus 2. So I change row 2 into row 2 minus 3 row 1. So I'm following a pattern. I want zeros to appear. So I multiply by 3 the first row, and then I subtract. Then I will do the obvious thing, which is divide by minus 2. So I get this shape here. And then have a look. I can get to this level here, right? So you see, I can get from A to a very special matrix. So you see, A and B are row equivalent if and only if B is row equivalent to the identity. So now I try to produce the identity from B, and this is the pattern I follow, okay? I hope you see that Cesare Piemontese, there is an idea, and the idea is try to go to some special shape. And the general idea is if A is invertible, the identity is the special shape. If not, well, we'll see in the future, because maybe they are not square, so they cannot be invertible, but still there is something nice we can do even in that cases. Okay, so now we start with B and we try to go to this shape here. So let me copy B for a second. So let's carry it with us here. And then I try to get the identity. So I have to get rid of these two. So the operation is to subtract to the second row twice the first. So to get 0, A minus 6, right? And now we see that something happens, because now if A minus 6 is different from 0, then B is row equivalent to 1, 3, 0, 1, which is row equivalent to the identity. If A minus 6 is 0, then B is row equivalent to 1, 3, 0, 0. And you told me this cannot be row equivalent to 1, 0, 0, 1 because of the 0 row here, which cannot appear in the second one. So you see, we found our answer. A and B are row equivalent if and only if A is different from 6, as some of you suggested at the beginning. And that's coming from what? Can you spot what is this number coming from matrix B? I write the conclusion here while you think. What is A minus 6? Is the determinant, exactly. So what is the idea? That to be a row equivalent, zero determinant can only be a row equivalent to some zero determinant. So whenever B has zero determinant, cannot be row equivalent to A because A is not zero determinant. And if you think a little bit more, it should be clear for a 2x2 matrix that if the determinant is not zero, then it is row equivalent to the identity. And so all 2x2 matrices with non-vanishing determinant are equivalent to each other because row equivalent, because they are row equivalent to the identity. Okay? So this is just a quick note. Okay, any question or remark? Okay, so now we move to something like this, 4.3, and I write down, say, system of equation like this to number 3. I write study for A in R, the system that now I copy. X plus 2y is equal A, ax plus 3y is equal 0. And what do we mean by study? Well, it means answer the following question. Do we have solutions? How many? Compute solution. Okay, so these are the 3 things that we want to do. Decide if there exist solutions, compute the solution, how many solutions. Okay, and that will depend on A. So let me know what you think. For what values of A are there solutions? How many? And can you find them? Okay, so someone suggests, so Giancarlo Sordone Herrera says that if A is not 0, then we can obtain a solution. And what is A is 0? What do you think? So Giancarlo Sordone Herrera says that if A is not 0, I can find a solution, but then you also need to find it, right? But it's not saying what happens if A is 0. Can you find a solution then? Good. There is the trivial one. Yep. Okay, so let's see how we can systematically do this. We don't want to do by trials. We want to use the associate matrix to the system. And see what we can do with it. Note that in this case, the system is not homogeneous. So we have also to be careful when we solve it, because we have also matrix B. So you see, we have a situation like this. Matrix B is not 0. So what happens? Whenever you apply an elementary operation to A, you will also apply the elementary operation to B, right? So people will say, well, then I work with a larger matrix, 1, 2, A, 3. I put some dashed line here to remember this is column B. So you see, this is something we will see in detail in the future, but this is just matrix A. And then you put also column B there, because when you apply an elementary operation to A, you also apply it to B. Simply that. Okay, so now look at this matrix. Usually it's called AB. And what is it row equivalent to? Well, I can do row 2 goes into row 2 minus A row 1. Note that there is no harm in using A equals 0 here. So we can actually do that. So 1, 2, A. Then I multiply the first row by A. I get A minus A, which is 0. I get 3 minus 2A. And then I get downstairs A squared. Okay? So let's see what will happen now. And Alireza Nafabadi found something that is not just enough to have A different from 0, right? Because you see, if this number is not 0, then I can divide by it and find a solution, right? So if 3 minus 2A different from 0, then my matrix here is row equivalent to 1, 2, A, 0, 1, A squared divided by 3 minus 2A. So, and you see, I now obtain the value of Y. And using the value of Y, I will obtain the value of X using the first equation. This happens if someone made me note that here it is not like that. It is 0 minus A squared. Thank you. So it is minus A squared. Thank you, thank you. Okay, so there is a unique solution. Okay, if 3 minus 2A is not 0, there exists a unique solution. And you compute it like this. X is going to be, sorry, Y is going to be equal to this number. And to find X, you simply use the first equation. What happens if A is equal 3 over 2? Then what I get here is something different. I get 1, 2, A, 0, 0, minus A squared, which in terms of system, it means my system is X plus 2Y equal A, 0 plus 0 equal minus A squared. So what do you think about solutions? Well, Giancarlo Sordones Herrera, the point is that 0 is not important here. What is important here is 3 over 2. Because it's not true that if A is different from 0, you have solutions. It must be different from 3 over 2. And if A is 0, there are solutions. And here, there is no solution. So what did we learn is that it's not always true that 0 is the crucial number. And how do you decide what is the crucial number? Well, doing elementary row operations. And there is a procedure for doing that we will see in a short while, which is just do elementary row operation to try and get to a triangular nice form. Okay. Any question about this? Beatrice Grassano, since the system is square, and since Cramer's rule is a theorem, and so it holds when the hypotheses are satisfied, of course you can use it. But you can only use it when the determinant of A is not 0, right? And it's probably not a big surprise that this is the determinant of A. So yes, you can use whatever you want, which is true, and you apply it correctly. But you need also to learn new tricks. Cramer's rule is a trick. Elementary operation is another trick. So you need to have many tools. The more tools, the easier it will be for you to find one which is adapting to your solution. And the more you know, the more ideas you made yours, the more likely it's going to be that you can come up with your own solutions, okay? Alberto Eusebio says something, if the determinant is 0, then A is not invertible, so we can bring it to the right. Is this the reason why? But if the determinant is 0, yes, you cannot find the inverse. And so you cannot apply Cramer's rule because Cramer's rule is multiplication by the inverse. Yeah. Roberta Papa says, sorry, can you show which is the solution when A is different from R over 2, 3 over 2? Yes. The solution in the general case comes from this one. So let's put it here. So how do you find the solution? Well, you see, the second equation is telling me that y is equal a squared over 2a minus 3. The first equation is telling me that x plus 2y, so 2a squared 2a minus 3, is equal a. And so this is how you compute y, and then you substitute in the first equation, you put it here, and then you compute x. So here are the solutions, okay? Okay, so any further question? No, Giancarlos Herrera. No, it's not. When you use elementary operation of type 1, A can be 0. The rows must be different. I is different from J, but A can be 0. When you multiply by a number, elementary operation of type 2, that number, which we call C, cannot be 0. Yeah. So A can be anything because you are not dividing by A if you think about it, right? You're multiplying, and you can multiply by 0. There is no problem in doing that. Okay, good. So we meet again next week, and have a nice continuation of your week. Bye.